Record. Now you may ask your question.
Okay, I was wondering how to do number 8 on the multiple choice.
Number 8 on the multiple choice. This one. Ha ha ha. Okay. So on number 8, they're talking just about this species, the CLO. And since it's being made in the first step and then used up in the second step, and that first step is nice and slow, and the second step is super duper fast, it means that whatever you are making is going to get used up really quickly.
Okay.
And so there's one where it's like the concentration is very low. Yeah, B.
At first I had thought it was D.
So it could fluctuate if they were both fast or they were both slow. Because we wouldn't know exactly how to compare the two of them. But because it's being formed in a slow step and then getting used up in the fast step, as soon as it's made, that fast step is going to go out and snatch it and use it up.
Okay, thank you.
Yup. All right, y'all. Let's since we started on multiple choice, let's go ahead and cruise through some more multiple choice, and then we can move on to the packet or free response in a little bit. So let's try and get all the multiple choice questions out of the way.
Did we do number 47?
Oh, yeah. 47. You got deep into your multiple choice. All right, 47. Oh, the isomerization of cyclopropene is a first order process with a half-life of 19 minutes. This time it takes for the partial pressure to decrease from 1 to 0.125. Okay. So something that we probably didn't talk a ton about, but is the fact that partial pressures or pressures are equivalent to concentration. Because for a gas, the pressure sort of controls its concentration. And so if I'm going from 1 atmosphere down to 0.125 atmospheres, and we're going through half-lives. So 1 half-life, I'd be at 0.5 atmospheres. 2 half-lives, I'd be at 0.25. 3 half-lives, I would get to that 0.125. So if I've gone through 3 half-lives, each half-life is 19 minutes. 3 times 19 would be 57.
Okay, thank you.
You're welcome. What next? Multiple choice. Holler them out.
Oh, sorry. You can go first. Okay. Can you explain 36 and 37? They're kind of similar.
Okay. I think I know which ones these are. Yes. Okay. So I'm going to start with 36. So actually, I'm going to open this on PDF so I can write on it. So on 36, they're asking us what the rate law should be based on that mechanism. And so to find our rate law, when we have a mechanism, we look up to and including the slow step. So in this case, that's going to be step 1 and step 2. If I just look at those 2 steps, I can see that N2O2 is acting as an intermediate, so it's going to get crossed out. So I look at just the reactants. in those two steps. N2O2 has been canceled out as an intermediate. I've got 2 NOs here, which means that NO is going to be second order. I've got 1 H2, which means H2 is going to be first order. And all you have to do is just compare it. So you would get C.
Okay.
37, I think, has the wrong answer in the answer key, because the answer should be A.
Okay, yeah, I was confused
Yeah.
because I got okay, so then it's good.
Yeah.
Okay.
So you
thank
do that one the same way.
While we're on those, can I ask a question about the equilibrium? Does it make any difference with the equilibrium and double arrows?
No. It makes a difference for some other things that we'll talk about when we get to equilibrium, but it doesn't matter right now. If you look up, like if you look up a video online of how to solve these mechanism problems, there's another way of doing this that's called the steady state approximation, where people do all this like you solve for K and then you substitute it into something else and you do all this crazy stuff. That is a good and valid way of solving these problems. AP Chem doesn't make you do that to get an answer. So it's not that it's a bad way, but it's just a way that you don't need to know how to do. And so I don't mess with it.
Okay, I have a couple questions from the multiple choice.
Okay, go for it.
Starting with number 6.
Robotics. Hello, number 6. Okay.
I was just wondering about the size of the catalyst. Does that matter?
Technically, yes. Wait, hold on. I'm thinking. Because if we change the size of any other particle, it will matter. So I assume, yeah, changing the size of the catalyst would matter. I lost my share, didn't I? So it should be all 3 of these. Answer should be E. Changing the partial pressure of the hydrogen, like I said, is basically the equivalent of changing the concentration of it, since it's a gas. And changing the particle size of the catalyst means that you've got more surface area on the catalyst, so it's able to interact with the reactants more, and so it's going to be able to make that reaction go faster. And then changing the temperature is going to make those particles have more energy. They're going to be able to exceed the activation energy to be able to make the reaction happen. So all 3 of those would be true.
And then my next question is number 16.
16. Okay. So we only have to worry about half-lives for first order things. They're all going to be the same. So that half-life is going to stay constant. If 87.5% of it decays, that means I have 12.5% that is left over, or that is still around. So just like when we talked about the other half-life problem, if I start off with 100%, after 1 half-life, I'm going to go to 50%. After 2 half-lives, I'm going to go to 25%, and then I'm going to get to that 12.5%. So that means 3 half-lives have gone by. If that total took 24 days for 3 half-lives, then that means each half-life is going to be 8 days.
So for the percent given, do we always subtract that from 100?
It depends on what they give. So this one says it's decayed. but we're always, anytime we do any calculations or we figure anything out, we're always talking about how much is left. So if they told you you had 87.5% left, then you wouldn't subtract it.
And then number 19. My question for that is, like, does reducing the volume not affect the rate in this case?
So in this case, it's not going to, because your reactants are a solid and an aqueous solution.
So it only affects it if it's gas.
Correct.
Can you do question 24, please?
24. All right. So 24, we've got this nice Maxwell-Boltzmann distribution showing up here. Temperature 1 is the solid line, temperature 2 is the dotted line. We got an activation energy marked on there. Based on the graph, which of the following statements best explains why the rate of disappearance of NO2 are different at temperature 2 and temperature 1? So when we have a higher temperature, temperature 2 is going to be the higher temperature because it's showing more particles down here at higher energy. And that also means that the area under the curve for that higher temperature shows that there's more particles above that activation energy. So when we increase the temperature, we increase the number of particles that can exceed that activation energy. So which one would that be? NO2 is consumed at a fast rate at temperature 2 because molecules possess energies would be A.
Why is it not C?
So fewer molecules do have higher energy at temperature 1. That part is true. But this part about favoring collisions between molecules rather than between the molecules in the container is untrue. Particles are going to collide with what they're going to collide with. And it's just as likely for them to bump into each other as it is the container. The temperature or the energy of those particles isn't going to affect what they're going to collide with. So the only thing that temperature is going to control is letting those particles exceed the activation energy.
Okay, thank you. Can you do question 48, please?
Sure. La, la, la. 48. The rate law for the reaction is found to be blah. By what factor does the rate of the reaction change when the concentration of both NO2 and Cl2 are doubled? All right. So if I have my rate law, and I'm just going to say that the concentration of NO2 is going to be X, and the concentration of Cl2 is going to be Y. I don't know. If I double both of these, so if I double what X is, and I double what Y is, because that NO2 term is a squared term, that means that's going to influence my rate by a factor of 4. My Y term is first order, so it's going to influence by a factor of 2, which means my rate is going to change by a total factor of 8.
For that
Okay.
one, sorry.
Go ahead,
For
Al.
that one, could you just plug in like two numbers, like
Yeah.
1 and 2?
Yep, totally.
Okay.
What else we got? Natalie, did you have another one?
Oh, no, I was just saying thank you.
Okay.
Can we do number 35?
35. Oh, that was, we did 36. Okay. Ooh, okay. So we got a picture here. We've got a ruthenium surface, and we've got a reaction happening on that surface. The rate of this reaction is determined by the amount of energy required to break the bond in nitrogen. This bond is weakened when the nitrogen is absorbed onto the ruthenium. Based on this information, which of the following provides the best reason for the use of ruthenium for the synthesis of NH3? I would say, I haven't looked at this question with anybody yet. The answer should be B. Am I right?
Yeah.
Okay.
Why is it not C?
So we don't necessarily know if that bond between the ruthenium and the nitrogen is actually stronger than the bond in N2. We just know that it helps weaken it when we absorb it onto the ruthenium. So by weakening that N2 bond, we're allowing this reaction to happen because we need that ammonia to be able to come in here and react. Or we need the nitrogen to be able to react with the hydrogen and make the ammonia. So by making this bond a little bit weaker, we're lowering the activation energy basically for this reaction. We're saying that we need less energy to be able to make that reaction happen. It might still be that that bond in N2 is still way stronger than the ruthenium nitrogen bond. It's just that if we lower that activation energy enough, it allows the rest of the reaction to occur.
Okay, thank you.
Yep.
Is this question like based on the fact that ruthenium is a catalyst?
Yep. So there's several different ways that catalysts work, and one of the ways that they function is they call them surface catalysts. So basically it holds everything in place and allows the rest of the reaction to happen. So instead of those molecules having to randomly find each other by bouncing, if you have a large surface of that ruthenium, those molecules are going to be able to attach to that surface, and then they're going to be able to find each other and react easier.
Can we go to question 43 and 44?
Ooh, double dip. Okay, 43 and 44.
For 43, I was wondering how you would determine the order, or do we just assume for half-life it's just going to be first order?
For half-life, assume it's first order. You can have half-lives for zero order and second order reactions, but AP isn't going to ask you about them. The other way that we know it's going to be first order is because for first order, half-lives are constant. They're always going to be the same. If you have half-lives in a second order or a zero order reaction, they actually change from half-life to half-life. So like if going from 100% to 50% took you 8 minutes, then going from 50% to 25% might take you 10 minutes. It's not consistent. But here we can see that this is consistent, because to go from 100 to 50% took me 3 days. To go from 50 to 25 took me another 3 days. So I can see that that's a consistent change in the half-life.
And then for number 44, I just didn't know how to do it.
All right. So this is kind of similar to the one we just did, where we talked about how the rate was going to change if you change the concentrations. So if they tell us that the reaction is first order with respect to X and second order with respect to Y, means that I know my rate law is X to the first and Y to the second. If my K is going to be constant no matter what, so to be totally honest, I don't even really need this math. When I plugged in 0.4 and 0.1, I got a rate of R. So if I plug in 0.2 and 0.2, now I could go through and solve for K, but that's sort of nasty to do when you don't have a calculator. You could do it, it's not that big of a deal. But by changing from experiment 1 to experiment 2, my X value got cut in half. So instead of X, now it's half of an X. My Y value doubled, so instead of Y, it's now 2Y. So the Y is going to make it increase by a factor of 4, but the X is going to make it be cut in half. And so my rate is going to be twice what it was in experiment 1.
Thank you.
Yep.
On number 55, I know it has to be like one of two. I don't remember which options they were because it's I don't remember if it's X or Endo. But why is it not C?
So, okay. So this is something we haven't talked a ton about. Because this is negative, that means that this is exothermic. So it means that D is out because that one is endothermic. We know we have 2 steps going on. So we need to show those 2 steps. So A is out. So let's see. Oh, okay. So answer is going to be B, because they tell us that first step is the slow step. And so that slow step is going to have the biggest activation energy of those 2 steps. So if I look at B, my activation energy here is this energy. My activation energy here is only that. Activation energy for my second step in C is this big. Activation energy in my second step here is only that big. So B is showing me the correct activation energies to have a slow first step and then a fast second step.
Okay, thank you.
Yep.
Can we do number 56?
56, yeah. Which of the following statements best explains why an increase in temperature can substantially increase the rate of a chemical reaction?
So this one makes sense to me, but I was curious about like D and E.
D and E are going to come later.
Okay.
So E, you know nothing about yet. D, technically we could talk about, because when we have these energy diagrams, right? The change in energy from my reactants to my products is my delta H. That's the change in the energy for the whole reaction. By changing my temperature or by adding a catalyst or changing any sort of other outside influences on my reaction, I'm not going to change the position of the reactants or the products.
Okay.
So that distance or that energy difference between the reactants and products is not going to change just by changing temperature.
Okay.
So
Thank
that's
you.
what, yeah, that's what D is saying.
I have an in general question.
Okay.
So does your rate law, like the constant, ever change?
The only thing, so the K is the same number for one given reaction as long as you keep it at the same temperature. And you're never really going to be asked to make a calculation for how that would change based on temperature.
Okay.
But that's why in a lot of problems, it'll say, hey, you do this reaction at 25 degrees Celsius. What is the value of K at 25 degrees Celsius? It seems sort of obnoxious and repetitive,
Yeah.
but they're sort of doing a cover their butt thing by saying, I want the K value of this reaction at the same temperature.
Okay.
So for partial pressure, are you saying that it's similar to concentration but for gas?
Correct. Because you're basically, if you increase the partial pressure, if you increase the pressure, you're either going to be adding more particles in the same volume, or you're going to be keeping the same number of particles but in a smaller volume. And so if our concentration is moles per liter, either way, we're going to be increasing that value. Anything else on the multiple choice right now?
I just was confused on number 22.
22. La, la, la. I need to make less questions. Oh, 22 is the one with all the words. Okay. Okay, so this is a tricky one. So what they're showing us in this first graph is that concentration of NO is decreasing, not in a zero order kind of reaction, right? Because we've got a graph of
right.
concentration versus time. It's a nice curve. We
Yep.
don't really need to worry about whether it's first order or second order, but just we see that non-linear change in concentration because of the stoichiometric relationship from our balanced equation. If my concentration of NO is going down, my concentration of O2 is also going to go down. Because every NO needs to react with O2. So since it's a 2-to-1 relationship, NO is going to get used up twice as fast. So between these two graphs, graph number 1 shows me that half as fast relationship of that concentration changing at the same time.
Okay.
Okay,
that makes sense.
So it has to be A. Now, because we don't know what order these things are, we can't really say anything about the rate.
Yeah.
In terms of, speeding up or slowing down or doing any of those sorts of things. But we can compare the two reactants to each other because they have to react in that stoichiometric relationship.
Yeah, I knew graph 1 was correct over graph 2, but I wasn't sure about the explanation or which exactly was the right answer. Thank you.
Anything else on the multiple choice?
Could you go over number 30?
Number 30, of course. All right, so we got a mechanism. Based on this mechanism, which of the following is the most likely reason for the different rates of step 1 and step 2? So step 1 is the slower step. So something about that must be more difficult or require more energy than step 2. So it must be B. So the only thing that's going to make reactions be either faster or slower than each other is that whole thing about collision theory, right? About we need enough energy to exceed our activation energy, or we need more particles to be able to make there be enough collisions. Something about step 1 is making those collisions harder to happen. And so the only choice of these options that really talks about that would be B.
Thank you.
Yep.
Could you please do 51?
51. Oops. Overshot. All right. What is the role? Oh, spark plugs. Okay. This is this is a very specific question. The spark plug in your car acts as a catalyst, basically. the little spark that the spark plug makes gives the combustion reaction of your fuel enough energy to exceed that activation energy. So it's not really a catalyst, then it's sort of just a source of energy, because it's not decreasing the activation energy, it's just helping you achieve that activation energy. So the answer should be C. There would be nothing that specific on your test.
Thank you.
Because wasn't there a question about enzymes too? I think we talked about that one in class. Like a specific
Yes.
question about how enzymes work. We're not going to be that specific. Right. Anything else on multiple choice? Going once. Going twice. Done. All right. Anything else about in general questions or something on some of the other work we've done?
I have a free response question.
Okay. Free response. Go for it.
In number 1, part B, I think. Yes. Why does increasing the concentration of the food coloring? Why is that the answer?
When the solutions are combined, the steam of the reaction mixture reaches absorbency 0 too rapidly. So basically what's happening is as that food coloring reacts with the bleach, if it's reaching an absorbance near 0 too rapidly, it means the reaction is going too fast. I don't know. Let's change the wording of that. It means that we're using up the reactants too fast to be able to make accurate readings. So if we increase the temperature, that's going to make it go even faster. And so we're not going to be able to read that one. We're probably not going to increase the bleach because they specifically say that the bleach is present in large excess. So adding more bleach is not going to change anything. But by increasing the concentration of the food coloring, we're providing more molecules of food coloring for that bleach to react with. If we're not doing anything else to change anything else about the rate that's going on, then by having more particles, we're going to be able to make measurements about that reaction for a longer period of time.
Okay. So it's less about the actual rate and more of how much you start with.
Yeah. So basically, even if it makes my rate go up a little bit faster because there's more particles, just the fact that there are more particles and I'm going to be able to see that reaction happen for a longer period of time is going to make it easier to make those measurements.
Okay. Because if you increase the concentration of the bleach, that would still also increase the rate, wouldn't it?
Technically it would, except up in the beginning above the graphs, it says the bleach is present in a large excess so that the concentration of that OCl minus is essentially constant throughout the reaction. So we have so much bleach in there that adding more in isn't really going to change anything.
Okay.
It's so concentrated that adding more in isn't going to effectively change the concentration.
Thank you.
Yep.
Can we go over question 3, part F?
Question 3, part F. All right. A second student does the experiment using a larger volume of peroxide. The student noticed that the reaction in beaker 2 proceeds extremely rapidly, causing some of the liquid to splash out of the beaker. Bad lab procedures. The student claims that as a result of the loss of the liquid from the beaker, the calculated number of moles of O2 produced is greater than the actual number of moles of O2 produced during the first 60 seconds. Yes, that would be true. So if we're thinking about, did they give us a reaction written out? They do. So if we think about this reaction, if as a reaction I am decomposing the hydrogen peroxide into oxygen, based on my calculations, I know I have a certain amount of this. I can stoichiometry it to figure out how much oxygen I should make in this reaction. Now, if some of that chemical splashed out, the actual oxygen that I created is going to end up being less. I'm going to be able to make less product because I actually had less reactant to make that happen. So compared to what the stoichiometry says, I am going to actually, in real life, right, the actual number of moles of oxygen is going to be less. And the calculated number of moles of O2 is going to be greater. The stoic version is going to be bigger.
Yeah, I kind of got confused with the calculated and actual.
Yeah.
part.
So anytime it says actual, they're talking obtained in the lab.
Can we go to question 4?
Yeah.
And then part C.
Yeah.
So for I wanted to know how can you tell what the order is from the graph?
So we know it's not zero order, because if it was zero order, a straight up graph of concentration versus time would give me a straight line of my slope. And I don't see that, so I know it's not zero order. So my choices are between first order and second order. And without, like, you could technically take the natural log of all of these data points and figure it out and see if you get a straight line. But a much quicker way is first order. We know we can talk about half-lives, and the half-lives of a first order reaction are always constant. They're always consistent. And so I can look and I could say, well, if I start with a concentration of 1.6, half of that would be 0.8. That happens in 8 seconds. If I go through another half-life, if I go from 0.8 down to 0.4, that also took another 8 seconds. So we see that that has consistent half-lives. So we know that that has to be first order.
And then for the double I part, that
Yep.
kind of goes back to what I asked earlier about, like, how would you know with the 99, whether to use the 99 or just the 0.01?
So yeah, so if it's 99% has decomposed, that means I have 1% left. So anytime I'm talking about a concentration, that's what I have left, because to measure that concentration that's sitting in that beaker, that has to be what remains.
Okay, thank you.
Yep.
I have a couple more questions on number 1. Or wait, never mind. It's part 2 or number 2.
Number 2. Okay. Oh, the pressure one. Okay.
Yes. The first question I have about this one is A.
Okay. So they gave us this data, says they're telling us that the reaction is first order. How is the data consistent with a first order reaction? Because no matter what my initial pressure or volume is, my half-life is the same.
Okay, so this is more of,
Yeah, because if you think about the equation for half-life, concentration, pressure, nothing is involved in that equation, right?
mm-hmm.
So first order reactions, they don't care what else is going on in your reaction. All they care is that their first order reaction, and that half-life is going to be the same no matter what initial concentration, or for this case, pressure, because we're talking about gas we start with. As long as that temperature is constant, which means that my K value is constant, it means my half-life is constant.
Okay. And then also C.
All right. The initial rate of reaction 1 greater, less than, or equal to the initial rate in trial 2. So trial 1 and trial 2, they have the same temperature, they have the same volume, but trial 2 has twice the pressure. So if we know we're first order, we know that by increasing the concentration, we're going to increase the rate. Because when we talk about our relationships, right, when I double the concentration for a first order reaction, I also double the rate.
Okay. This one I might have just been confused on because of the pressure.
Yeah. So remember that we can treat pressure just like it is concentration.
Okay. Thank you.
Yep.
Can we go to number 10, part C?
Yes. 10 part C. So this is kind of weird.
A little bit.
So let's talk about this in a different way. So if we have our rate law, I think they made this way more complicated than they really needed to. Because notice that the rate in the chart or in the data table is for the formation of NO2. Usually instead of rates of formation, they usually talk to us about the rate of disappearance of the reactant.
And that's when you would just plug in like one of the values.
And that's when we would just plug it in. And I'm pretty sure if you just plug it in, you get this number.
Oh, when I plugged it in,
Is it not?
No.
Okay.
It's like nowhere close. Maybe it was just me, but
Well, hold on. Okay. So let's go and bust out the old handy dandy calculator. Take that squared times that. 8.52 times 10 to the negative 2 divided by that. That's what I got. So I took this rate law and I just plugged in data from the first experiment.
okay.
And so I said 8.52 times 10 to the negative 2 molarity per second equals K times 0.02 squared and 0.03. And I got 7,100, which is that 7.1 times 10 to the 3.
Okay.
And then units would be 1 over molarity squared seconds.
Okay. I'm getting that now.
Okay. It might be slightly different if you use a different experiment.
Yeah.
Like if you use experiment 2 or 3, it might change the number a little bit. But as long as you're using the data the right way, you'd still get credit for it.
Okay.
Can you do number 6, part E?
Number 6, part E. Okay, so here's 6. Are you okay with the activation energy part?
I
Or-
think you might have just taken it out.
Did I take it out? What was E?
Draw a circle around each of the quantities below that
Oh.
has a different.
Yeah, it's right here.
Oh,
Evidently.
that just doesn't have an E on it.
Evidently, I changed the number somehow. Oh, does it go D, E, F? I wonder
Yeah.
if I changed that. Okay. So the only thing that a catalyst is going to change is the activation energy. And that's what that little EA means. We haven't talked about K is about equilibrium and delta G is a thermo thing. We haven't talked about that yet. And we talked about this earlier about how the delta H is that difference in energy between the reactants and the products. And so
Okay.
that's not going to change when you add a catalyst.
Thank you.
Yep. Anything else on the free response? Going once. Going twice. All right. So we're down to any questions about the packet or in general or anything else?
Can we do mastering chem from
Ooh,
last week?
from last weekend, yeah. Let me get signed in. I know there were a couple weird ones on there. Come on, baby. You can do it. Come on. There we go. Okay. Do you know which problem it was?
Number 8.
Oh, buddy, this is low. Okay. All right. So we know we have a second order reaction. They tell us our rate constant K. If the initial concentration is 2 times 10 to the -5, how long will it take for 90% of the reaction to disappear? Okay, so this is anytime we're talking about time, the only equation that we have that has time in it are those integrated rate laws, those ones that are on your blue equation sheet. So they tell us that we've got a second order reaction. And so the equation for second order is that 1 over concentration at any time minus 1 over the initial concentration equals positive KT. So they gave us a value for K, so we know what to plug in there. T is what we're trying to solve for. And they said 90% of the reaction to disappear. So I'm starting off with 100% of a reaction. And if 90% has disappeared, then my concentration that's sitting in that beaker is going to be 10%. So then I can solve for T.
Yeah, I thought I was supposed to take it and then like multiply it by the initial concentration because it said like something percent disappear. I
We
just
can
take the percent.
we can just stick with the percents if we need to. If they didn't give us a percent, I mean, technically you could take 10% of this initial concentration and plug it in there. But that's extra work. If they didn't say it was 90% disappeared, if they said, you know, how long would it take to get to a concentration of 1 times 10 to the negative 6th, then we could just plug that value in for our final concentration.
And then can we do question 11? I
Okay.
didn't know how to find the order for it based on the chart.
So if you have a graphing calculator, I'd plug it into your graphing calculator. And do the natural log versus time and the 1 over concentration versus time. Not necessarily thinking to plug that into your graphing calculator, maybe. Just like we talked about one of the multiple choice questions about looking at the jumps. So we see that our time data points are evenly spaced. We need to figure out which one of these is going to give us evenly spaced concentration data also. So we can see that this straight up concentration is not evenly spaced. It starts to get really, really, really small jumps towards the end. So you could take the natural log of, and I wouldn't do all of them, but maybe do the first 3 data points or 3 or 4 to see. So if you did 4 data points, you could check 3 jumps and see how consistent they were. And that would help you figure out what order it was.
Can we look at that and do it, the thing where it was like if the half-life, can we do it
Oh,
based
maybe.
on that?
Oh, let's find out. So half, I don't know if they gave us enough data to get that deep. Let's find out. So 0.95, half of that would be 0.475. So it's not quite exactly what they gave us on here. Because half would be 0.475, so it'd be close to 50 seconds. And then if we cut that in half again, it'd be 0.23, which again isn't exact, but it's close to this. And we can see that that's definitely not an even jump. So from 0 to 50 and then 50 to 150. So those are not even half-lives. So yeah, you could do it that way too.
Thank you.
Yep. Anything else? We got a couple more minutes left. Nothing. Going once. Going twice. All right. Got any last minute questions? You can ask tomorrow at the beginning of class. But since Wednesday's short schedule, I want to make sure that you guys have enough time to get through your test and to get the whole 40 minutes done. So have a good night, get some sleep, and I'll see you all tomorrow.
Thank you.
Welcome. Bye, y'all.
Thank you.